So in the second hour, actually, what I want to do is start on the kind of really fun thing that came out of Maxwell's equations, namely electromagnetic waves. Okay, so Maxwell's equations, we're talking what? We're talking 1865, 1867. The demonstration of the existence of electromagnetic waves was only done by Hertz, 2 decades afterwards, the late 1880s. So let's just discuss how Maxwell's equations themselves contain naturally solutions in terms of electromagnetic waves. Right? So let's see what we have. I'm going to emphasize as a starting point in vacuum. So here we have no charge density and we have no current density. There's just nothing, right? What do we have in that case? Our equations look like this. Divergence of E is equal to 0. There's no charge, so Gauss trivializes. We've of course got that the divergence of B, as always, is equal to 0. Then we can write it this way: the curl of E, I'm now going to put the term on the other side, derivative with respect to time of B, that combination is equal to 0. And once again, Ampere Maxwell, I can rewrite as the curl of B, and now minus mu 0 epsilon 0 dE dt is equal to 0. So these are our 4 Maxwell equations in vacuum. What's the characteristic of these equations? Well, 2 of them are rather trivial, but the other 2 are coupling the electric field and the magnetic field. These are first order differential equations, but coupled. And we should be able to rewrite these as uncoupled second order differential equations. Okay, essentially substituting one into the other. So how are we going to do that? Well, so let's just take the curl of this one. So what we're going to do is we're going to take the curl of that whole thing. Why am I taking the curl of this whole thing? Because I'm aiming for the curl of B. And once I get the curl of B here, like I get immediately, I'll be able to use this one here. Okay, so so that's what I'm going to start with. So what does that give me? First of all, let's do it step by step. Curl of E, and then I'm going to have a d dt of the curl of B. Okay, so you've seen this one already. This is just going to give me mu 0 epsilon 0 dE dt. So this whole second term here just becomes mu 0 epsilon 0 second derivative of E with respect to t. Okay, and for this one here, essentially I need to use an identity that tells me that the curl of a curl is the grad of div minus the Laplacian. Okay, that's just a vector identity that's tabulated at the end. You can work it out component-wise once in your life if you want. It's just the way the coefficients arrange. Now, the point is that now we're in vacuum, and Gauss tells us that this divergence of E is equal to 0. There's nobody there. Question? Is that a second derivative from the bottom right? Okay. dt squared. Thank you. Yes. Very good. Okay. So this one is 0, and I'm only left with this Laplacian of E like this. So what I get is that the Laplacian of E is equal to the second derivative with respect to time. Okay. And actually, we did it for E here. However, I can do absolutely exactly the same derivation, starting from the curl of this one, and then using the same identities and going the other way. And then what I get is the same equation for B. Okay. So I get these wave equations. In vacuum. How much have you studied wave equations like this? So don't you have a course like called wave physics or something? Or, what is it called? Trillingen and Holfer, that's it. That's okay. So when you see such an equation here, you should have the reflex of telling me what the possible solutions are to that thing. And let's see if you can tell me. So what is a form here that would solve this this equation? How general is it? Huh? Combination of cosines and sines, and do I have like much flexibility in choosing those sines and cosines? So so maybe we can do some examples to be clear, and then we'll make a statement about the general form that solutions can take, right? So yeah, maybe quickly. So any form, let's write it like this: E of R and T is equal to some constant vector. So this is some constant vector. But now I'm going to put some dependence, e to the I. I'm going to choose a direction k dot r minus omega t. Okay. So any form like this, it works if I choose this this omega to be c times the absolute value of k, like this, where c is the 1 over the square root of mu 0 epsilon 0. Okay, so a few comments. So when I take the maybe we can even do it in one component to make it absolutely transparent. Yeah, maybe that's the best way to do it. Okay, let's just do it